So this is a subunit of the properties of matter, that is the 10th unit, right? Uh, so this is about a layer that is on any liquid. When you consider any liquid, there is a layer on the free surface of any liquid, right? So for an example, if you take a needle and carefully you can place that needle on the water surface. You might have seen that, right? Take a needle and you can balance that on a water surface. You know that the density of a needle that is made of iron, right? It is more than the density of the liquid, that is water. So it must sink. Since its density is high, it must sink. But that does not happen. Why? Because over the liquid surface. So if the liquid surface is like this is a cross section, you can place it. You can place a needle like this. It doesn't sink. The reason is this is the free surface, this is water, this is the free surface. This behaves as like a cloth, right? So you can place it. So this is true for any liquid. The solids does not have this property. Any liquid has behaves the free surface as like a kind of like a skin, right? Kind of like a skin. Another example, an insect can walk on this. You know, insect is also heavy. The insect does not sink. So this is not the effect. The reason is not upthrust. The reason is surface tension, right? You know, upthrust cannot balance this like this, right? There are other reasons. If you think about a water drop, it takes the shape of a sphere. The reason is this is the water free surface. This free surface acts as a free surface acts as a skin, right? So this is like a sac. So inside it, it is a liquid. The skin also made of liquid. But due to this surface tension phenomena, what happens is any liquid surface behaves as kind of like a skin, right? Elastic skin. Okay. So here it is a very important concept in physics that you have to understand when it comes to surface tension, right? So those are the evidences that surface tension exists over any liquid surface. There's surface tension, right? Okay, first write down this note. Write down small insects, small insects, small insects walking on water. Small insects walking on water, comma, final water drop, final water drop, hanging by the end of a tap, hanging by the end of a tap. You have seen this, right? So if this is a tap, there's a drop remains at the bottom, right? Comma, small raindrop, small raindrop, take in, small raindrop, take in shape of, take in a spherical shape, taking a spherical shape, comma, soap bubbles having a spherical shape, soap bubbles having a spherical shape are evident that surface of a liquid behaves as a stretched elastic skin stretched elastic skin. So as I'm giving you the note, you have to understand, right? And if you have any problem, send me a message, right? Okay. So now you know that there is something called surface tension over any liquid. There's something called surface tension over the free surface of any liquid, right? And it behaves as like a stretched elastic skin, like a balloon, right? Kind of like a balloon, right? Uh, so then you have to understand why this happens. Using intermolecular forces. You know that when you think about water molecules, if you know learned chemistry, between each molecule there's an intermolecular force. Between each water molecule there's intermolecular forces, right? So that we can explain this phenomena using intermolecular forces, right? Write down the subtopic surface tension. Write down surface tension based on molecular theory. Surface tension based on molecular theory. Okay. You can draw this with me, not this one. So here you have a liquid surface. This is a free surface of a liquid, right? If you consider a water molecule inside the liquid, so this is the water molecule. Adjacent to that, there's a water molecule, and it exerts a force like this. That you can see, right? To this direction. And surrounding that water molecule, there are other water molecules. And symmetrically, these forces are acted on this water molecule, right? Here you can see all these forces are balanced. Then you can draw like a sphere, right? Using if you can contain all those forces in a sphere, and it is called sphere of influence. It is called sphere of influence. Draw this with me, right? Sphere of influence, right? So any water molecule inside the liquid is balanced, like they are in equilibrium, right? Those water molecules are in equilibrium, so they are not under any tension, right? But if you consider something like this, a water molecule on the free surface here, intermolecular forces acts only like this, right? Like this. Here to this to horizontal side they cancel off. You can see there is an unbalanced force downwards, right? Because here we might have air. Between air and water molecules, we have a very weak intermolecular forces, so we can neglect that. So there are no forces here, right? Only on the water molecules on the surface, there's an unbalanced force downwards. So what happens is, this unbalanced force pulls the water molecule downwards. So to prevent that, this surface creates these forces, surface tension forces. These are called, this is what we are going to learn here, right? This pull towards the liquid is what causes this surface tension to occur, right? Surface tension to occur. So that is all you need to know, okay? Right. Take this down and thumbs up once you've taken this down. And if you have any problem, let me know. Right. Write down point below this right here. Write down since intermolecular forces spread in a small range, spread in a small range, influence of it is in a small distance. Therefore, to the same line, right? To the same line. Therefore, a molecule is influenced only by the molecules around it. A molecule is influenced only by the molecules around it in a sphere. Which is called sphere of influence. This word is important, right? Sphere of influence. In Sinhala we call that Kadaim Golaya, right? This is a sphere of influence. Okay. Then next point, write down the next point. A molecule like A, so this is A, right? This is molecule A. Write it A, right? A molecule like A comma completely immersed in the liquid is applied to forces by surrounding molecules comma causing the net force causing the net force on it, net force on it to be zero. Net force on it to be zero, right? Okay, that is the second point, right? Then the third point, write down. If a molecule near the free surface, so that is, we call, let's say B, a molecule near the free surface is considered, comma, number of molecules above the molecule, number of molecules above the molecule is less compared to, number of molecules below it, So as you are writing the note, try to understand, right? Number of molecules below it. Okay, full stop. To the same line, right? So the net force on the molecule acts downwards. As this occurs to all the surface molecules, the surface stretches, the surface stretches, which causes a tension over the surface molecules, right? Done? And if you have any problem, ask me, right? So far we have discussed the evidence to the surface tension, right? So those examples, why you can place a needle on a liquid surface. Reason is not upthrust, reason is surface tension, right? Why an insect can walk over a liquid surface. Why a soap bubble takes a spherical shape. So those examples we will be discussing as applications, right? But before that, we have to know how to quantify the surface tension using equations, right? So we learned those examples, then we learned how that occurs using intermolecular forces. So you need to have a brief understanding of these intermolecular forces as well, right? Then that's it. After that, we are going to define surface tension, right? Okay. Write down the subtopic. Definition of surface tension. Okay, now this is good stuff, right? Actually now, previously it is like an introduction. Actually now we are starting surface tension, right? Right. Write down the subtopic, definition of surface tension. Before that, sorry, after that definition of surface tension, uh, let's draw this one. Draw this with me. Draw a line like this, like inclined line, right? Then this is how surface tension forces are acting on this line. Actually, they are perpendicular, but this is a 3D image, right? So you don't see that, right? So these are surface tension forces, right? And this is a liquid surface. Do you understand that? This is a liquid, this is a 3D image, okay? If you draw a line, an imaginary line, on a liquid surface, perpendicular to that line, there are surface tension forces like this. Okay? This is a liquid surface. And you can draw any line you want. And if you draw any line on the surface of an imaginary line, these are not actual lines, right? If you think about an imaginary line over a liquid surface, perpendicular to that line, there are surface tension forces acting on, like this. Understood? Right. Draw this. If you are done, thumbs up. Navindi, are you done? Right. Okay. Below this, right? So this is the definition, right? Below this, right? Force acting alone, force acting alone, force acting along the surface of the liquid, surface of the liquid, surface of the liquid on a unit, on a unit length of, on a unit length of an imaginary line, on a unit length of an imaginary line drawn on the surface of the liquid, drawn on the surface of the liquid, comma, normal, to, normal to, and towards one side of the line, towards one side of the line, is equal to surface tension, surface tension, right? Here, I think done, right? Right. Here we have to define surface tension, right? But if you take both forces, those forces are balanced. So you get a zero value. So what do? There are some rules, right? So you have the line on the surface. You have to carefully understand this. They ask in the exam, right? There's an imaginary line on the surface of the liquid and perpendicular to it. But you don't consider both of these. You consider only one side. Why don't we consider both sides? If we consider both sides, these forces cancel off, right? So we only consider one side. Let's say if you take the resultant force of all these surface tension forces, let's say you get capital F. draw this as well, right? So according to the definition, T is equal to force. You don't consider all the forces per unit length. So you have to divide this by the length. Length means this length, right? From here to here. You consider the total force on the line, perpendicular to it. Total force on this line, then you divide that by the length of the line. Then you get surface tension, right? So in most cases, you need this force, total force. So you can have an equation, cross multiply, F equals TL. To one side, this force is equal, surface, this is actually a coefficient, right? We call that surface tension, right? We are not going to say surface tension coefficient. We just say this surface tension. Surface tension, so that is a force per unit length. Force per unit length, but under these conditions, right? On the surface, perpendicular, over the surface, to one side. Then divided by length. So you get surface tension. So, but the useful equation is, in most cases, this force. We need to figure out this force. So, what do? We just have to multiply surface tension by the length we consider. You'll understand when we are doing problems, right? What this means. Okay, take this down. Then let's think about dimensions. Dimensions of surface tension. Right? So find the dimensions of surface tension and let me know. You can write it here. So that is, so it is force divided by length, right? Yeah, it should be mt minus 2. So here you have mlt minus 2, that is dimensions of force divided by length. So you get mt minus 2, right? Then there are some units. So what should be the fundamental unit? Based on fundamental quantities. So m means kilograms, t means time, so kilograms per square second, based on fundamental units. Just take this down, you know this stuff, right? Then we'll think about derivative units. Here, force divided by length. What is that? Newtons per meter. You can have newtons per meter. Then there is another unit. You still don't know that. I will teach you later. Joules per square meter. There's this unit as well. We'll use this later, right? Joules per square meter. For now, just take it down. Thumbs up if you're done. Right. So now we have an equation for surface tension, right? It will be more clear as we are doing questions, okay? Right. For now, remember this equation. F equals surface tension coefficient times L. We call this surface tension, right? So T is force per unit length. So the definition of this length you have to understand, right? There are conditions. This is not just a length. One side, perpendicular, over the surface, those conditions. Right. Another thing you have to understand, this surface tension coefficient, I'll call surface tension, okay? Surface tension So what could happen when as the temperature increases? What do you say? Does the surface tension increase or decrease? If temperature of a liquid increases, what can happen? Yeah. Surface tension decreases, correct. Right? You can guess that, right? It has to it has to decrease. Meaning the surface gets weakened with the temperature. As the temperature increases, actually when you place the needle on the liquid surface and you, let's say you increase the temperature, after a while the needle would sink. Why? Because the temperature, the heat decreases this T, capital T. Okay, write down topic, not a topic, like a point. You just have to know that, right? Write down when the temperature of a liquid, point, right? When the temperature of a liquid increases, when the temperature of a liquid increases, comma, comma, surface tension decreases. Surface tension decreases, comma, since surface tension decreases, since intermolecular forces weakens, intermolecular forces weakens. So if you know chemistry, you know that intermolecular forces kind of like weakens, right, with the temperature. So then there's this graph for a considered liquid. Draw this graph with me. Y-axis has surface tension, newtons per meter, not square meter, right, per meter. Here you have temperature. Let's say centigrades. So as the temperature increases, surface tension, this is surface tension, decreases. Shape is somewhat like this, you have to remember, right? The reasons we don't know, we don't go in that much in depth. You just have to know this graph, right? And there's a special temperature where the surface tension becomes zero. Surface tension completely goes out, right? That temperature, we call that critical temperature. Just take it down, critical temperature. So this is stuff you just have to remember, right? We are not going to do problems using this. I mean, we are not going to explain why it takes this shape. We don't go that much depth. Actually, depending on the liquid, this shape changes, right? For most liquid, this is the shape. For any liquid, it decreases, right, with the temperature. Okay, take it down. Thumbs up if you're done. Right. So now we know surface tension depends on temperature. You just have to know that, right? There's another thing that surface tension depends on. Write down another point here. Write down surface tension depends on cleanliness, and other medium in contact with liquid, right? So let's say you have water, and let's say you put some dirt over the water surface, right? What happens is surface tension drops. It is less clean, right? Because it has dirt, right? Surface tension changes. Right. Another thing is usually there are like two mediums. When it comes to applications, there are like two mediums. Like let's say you place water on a glass sheet, then the surface tension is a one value, right? Then let's say you place mercury like this, right? First, just take this down. These are examples. Then you will understand, right? Example. First one. We are thinking about one temperature at 20 centigrade. Just a one temperature, right? Because with temperature as well, this changes. So we are keeping temperature at a certain value. Write down example at 20 centigrades, comma, water in contact with air. Water in contact with air. Water in contact with air. In front of it, right? This value 7.2 minus 2 per meter, right? Not a square meter, newtons per meter, this value. Then second one at the same temperature, write down mercury, right? Mercury in contact with water. Mercury in contact with water. Here water with air, right? This value. When we have water and air, we have this value. Here we have water and mercury in contact. Then for water, that value is this much. Newtons per meter. Take it down. Okay. Right. So try to remember this value. In the exam, they give you this value, right? Usually you get problems. There's water and there's air, right? So it is around this value, right? 7.2 times 10 to the power minus 2. It's better if you can remember, but it is not necessary, right? In the exam, they give you this value. Minus 2 newtons per meter, okay? You just have to understand with another material. If water is in contact with another material, it is a different value, okay? Right. Then another point. So these points are important when you are doing problems, right? So I am building you up to that, right? Step by step, okay? So listen carefully. Another point, write down. A liquid drop. A liquid drop, comma, a liquid drop, comma, an air bubble, and a liquid drop, an air bubble in a liquid has only a one free surface. Has only a one free surface. Has only one free surface. Okay. Below that, leave like uh, 3 lines, right? Below that sentence, leave 3 lines. Then you start this point, another point. First, first point, then leave 3 lines, another point, right? Write down a soap bubble, a soap bubble, a soap bubble, comma, a soap layer, a soap layer has two free surfaces, has two free surfaces, has two free surfaces. Okay. So when you are doing questions, this is a very important point. Many like forget this, right? Then you get the wrong answer. You have to know a liquid drop or an air bubble inside the liquid, right? Or a liquid surface only has one free surface, right? So this is what it means. So below the first line, you can write, you can draw this. So what is this one? This is like a raindrop, right? It takes a spherical shape. So what do you mean by a free surface? This is the free surface, right? So you can see there's only one free surface. This is a liquid drop, like a raindrop. It only has a one free surface. Then another one. There's liquid outside. This is air bubble, right? So inside it, it is air. So how many free surfaces that when changes the medium? Only this one, right? Only this surface. Understood? One free surface. Then if you think about so a liquid in a vessel, this also only has a one free surface. This also has a one free surface, right? So you can understand what free surface means. Okay, you can draw this below the first line. If you have done thumbs up. Quickly, right? Right. So the another one under the second point, now we are considering a soap bubble. Soap bubble. This actually has two free surfaces. So one surface is here, another surface is here. Do you understand that? When you consider the surface, it is made of a liquid, right? This surface is a liquid. So there is air here, then liquid. Again you have air and liquid. Again you meet, these are like interfaces, right? Here you have to go from air to liquid. Then again go for liquid to air. So there are two surfaces. Another thing, let's say you can make this soap layer. Again, what do you have? I'll draw a cross section of that. This is liquid layer, right? I mean soap layer. Here you have to go from air to liquid. Then again, liquid to air. So here also there are two surfaces. One surface is here, one surface here. Just draw these. This is below the second line, right? Second point. I think now you can identify how to get those free surfaces. But here what do you get? Here air, then liquid, only one. Here liquid, air, only one. Here air, liquid, only one, right? But here you have to go from air to liquid, then liquid to air, right? So in these cases, you have to double the equation, right? We'll see how to do that as we are doing questions. Right, then write the subtopic. This is a main subtopic. Write down surface energy. So up to now we talked about surface force. Then we are going to define this using energy, right? Energy, right? Write down subtopic surface energy. Surface energy. Write down below that, right? Let's consider a horizontal wire frame. A horizontal wire frame A B C D, capital, right? Wire frame capital A B C D, and a straight wire and a straight wire XY, straight wire XY. Sliding on the frame. A liquid layer is formed on BXYC, right? Okay, right? Done. Okay, so you have this wire frame, right? So this is ABCD. This is a rectangular shape, ABCD, but we don't have here. Then this XY wire you can actually slide over this too, right? Then you make what? A liquid, you can make like a soap layer, right? Let's say you make a soap layer here. Then what do you have? You know that here there are surface tension forces acting to this side. Okay, acting to this side, I mean over the surface. You know that this has two free surface. So this is so over a one surface, these are the surface tension forces. There's a surface below this as well. Then the surface below as well, I'll mark those forces, use a different pen, right? There are these surface forces. Understood? So this is a liquid layer, like a soap layer. It has two free surfaces. Above surface, I mean top surface, top free surface. We have these surface tension forces. Below that, bottom, it's like this, right? Cross section. There are forces here. Then there are forces here as well. So use a different pen to draw these forces. Okay, quickly take this down and thumbs up once you're done. I'll explain. If you have any doubts, let me know. You need to understand this 100%, okay? So without understanding this, you cannot go to problem solving, okay? Others, if you are done, thumbs up. Jans, are you done? Right. So let's say you made a soap layer like this, right? Soap layer like this. Then what do? We apply a force to other side and we bring this wire from here to here. These are dashed lines. Let's say that position is x dash, y dash. Okay. So what do you see? The area of the soap layer has increased by, let's say, delta A. You can mark this. Area has increased by delta A. And let's say the distance the wire carried is simple x. And the force applied, we apply this force, right? Let's say that force is capital F. Right. Below this, write down. Let's say the wire is carried. Simple x distance by applying capital F force, comma, capital F force, comma, isothermally. So what is isothermally? You have learned thermodynamics, right? Isothermally means constant temperature. X distance by applying a force capital F, comma, isothermally. So why do we bring this isothermally? Because while we are doing this, we need to keep the temperature constant. Okay, otherwise surface tension changes. And the other thing is we won't be able to define this one because so we are doing work, right? By applying this force, we carry this to x distance. So how much is the work we have done? Fx, right? Force multiplied by the distance. displacement, Fx. So that work is stored in this liquid layer. So that is what we call surface energy. So if we find this work, that work is equal to the surface energy stored in this. Work is converted into the surface energy. But if the temperature change, any point means where? Before surface energy? Okay, after the diagram. Right. So we apply a force capital F, right? Right? Just leave it here for now, right? Then I'll explain. You apply a force and bring this wire to x distance. So the work done is Fx. That work done is stored in the liquid as surface energy. If there's a temperature change, meaning of that is part of that work done has dissipated as heat. But when we say isothermally, we assume that there's no heat dissipation. The work done is completely converted into the surface energy, right? So that way we can define equation for this, right? Then below this, write down surface tension, surface tension, force applied by a one free surface of liquid layer equals TL, right? So tension times length. Let's say length is L. So that is TL, right? To this side. Here the sentence, then it is equal to TL, right? Do you understand that? It is from a one surface, top surface, right? Top surface of the liquid layer. So one force is T, you have to multiply that by this length. So you get the total force by a one surface. One surface is mean top surface. Then below this, right, surface tension force, surface tension force, surface tension force. Similarly, right, surface tension force applied by both free surfaces equals to what? 2TL. So then we consider both surfaces, this surface and this surface, TL, TL. We have 2TL, right? Below that, right, therefore, force required to be applied to move the wire, XY, to move the wire XY at constant velocity, at constant velocity, within brackets capital F equals, it should be equal to what? You need to apply 2TL, right? Okay, if you have a problem, ask me. Okay, so I'll explain this further. Listen. There are T forces. There are two free surfaces, right? One surface to another surface. Top surface, how do you get the force, total force? You just have to multiply T, that is surface tension coefficient, by the length, simple L. So that is, you have TL to this side, right? Then there's a bottom surface. So for that also, there are surface tension coefficient times length. Again, you have TL. Then what do? You need to bring this wire at constant speed to this side. What do you have to do? You need to apply a force capital F to this side, right? So what happens? Here you have the wire. So the wire is balanced. Actually, it is being brought at constant speed. Then this F is equal to required force is, total force is equal to 2TL. Okay? I think you understood that. Okay? So you can further study this, right, on your own. Then it will be clearer. Okay, below these, write down work done, work done, work done. So W equals Fs, right? Work done, W equals Fs. Okay. So what is what is force? 2TL, right? F is 2TL. Then what is the distance? S, that is simple x. Okay. Then I am taking T in front. Then put 2 here, 2Lx, right? Then we can say this 2Lx means what? Length time x. So we have surface area, increase of surface area. But there are two surface areas increase, right? Top surface, bottom surface. I'll take it as a 1, right? So let's say that is delta A. Delta A. So delta A means what? 2 times this area, right? Here delta A means not only this surface, this one and bottom one, top one and bottom one, right? So I'm taking it as a 1 delta A, right? So depending on the question, you can figure it out, right? So this is actually the increase of area. So that is delta A. Then W equals T times delta A. So this much of energy is stored in this liquid layer. Take this down and thumbs up once you're done. These are really important, right? So it is twice the area, but I just used only a one term here, right? T delta A. Others done? If you're done, thumbs up. Okay, so clearly you have to know what this delta A means, right? That is the total increase of area, both top plus bottom areas, right? Right here, delta A, change of area, actually it should be change of total area, right? Change of total area of free surfaces. Change of total area of free surfaces. Okay. So T times area, right? Delta A or area. In this way, you can find the energy. How do you find force? I mean, force due to surface tension, T times length. This is force. So you get newtons per meter, right? For tension. Here you have energy is equal T times delta A. Here length, here area. So you get what? For this one, you get joules per square meter. Now, do you understand why that unit comes? Where that unit comes from? Same units, right? Same units. But here it's based on energy. Here it is based on force. Okay. You don't have to write that. Below this one, write down. Surface energy increases by the same amount as the work done by the same amount as the work done as the same amount as the work done, right? So since we did this isothermally, that W is equal to stored energy. Otherwise, there's a heat dissipation. There's no heat dissipation, right? So we can have, if we did that isothermally, we can write delta E is equal to T delta A. I mean, the work done is completely converted into the surface energy, right? So delta E also is equal to T delta A. But under what condition? Isothermally, right? Okay, write this down. Delta is equal to T delta A. Then based on this one, you can define surface tension. Delta E divided by area. So you have this unit, right? Joules per square meter. Take this down. Thumbs up if you are done. Below that equation, write down. Below that equation, Therefore, capital T can be considered as work required to work required to work required to increase work required to increase the surface area by a 1 unit by a 1 unit by a 1 unit. Okay, so what is this? Previous equation is what? Force per unit length. This equation, energy per unit area. Understood? You have to understand that pattern, right? Okay, below that sentence write down, when surface area increases, when surface area increases, when surface area increases, comma, surface energy increases. Surface energy increases. So what is the example that surface area increases? Below this write example, write down a large liquid drop breaks into a large liquid drop breaks into small drops isothermally small drops isothermally. Example, a large liquid drop breaks into small liquid drops isothermally. So in that case, surface energy increases, right? So does actually the surface area increase in this case? Huh? Here what happens? A large liquid drop breaks into small drops. Have you learned in like O levels, right? When you have like a let's say a large ice cube, I think you have learned that in I mean heat as well, right? Thermal physics. In practicals, they ask why you are not given a, so you need ice cubes when you are doing practicals. You are not using large ice cubes. What do you use? You have to smash those ice cubes into small pieces. You use these ones. So they ask what's the reason? These ones quickly dissolves into water, right? Small ice cubes, these are actually ice like, right? Yeah, ice chips, yeah. You use ice chips, good. You're not going to use ice cube there. But why does this like dissolve quickly into liquid? Here, surface area is higher, right? That's the reason. When you take the total surface area of these ice chips, it is more than surface area of this here, right? Why? Here you have what? When you crack this, you have these areas as well, right? Let's say you crack this like this. this area plus these small areas as well. So you can see the area has increased. So when you make it to small parts, let's say a large water drop into small water drops, surface area increases. Then also you can collect all these and make a large drop. In that case, surface area decreases, right? So surface energy also decreases. Just remember that, right? I mean, you have to understand that. Yeah. So that's the reason there, right? That's why ice chips dissolves quickly, because it has more uh, contact area with the liquid, right? Rather than here. So area here is higher than here, right? Okay. So to demonstrate this, we'll do a question, right? Write down Q at the note, right? Note. Write down Q. Find the work required. Find the work required find the work required to break a water drop of 4 millimeter radius 4 millimeter radius into 1 millimeter radius drops into 1 millimeter radius drops. If you want, you can draw a sketch. So what do we do? Listen, right? You have a 4 millimeter. You can try this later again, these questions. You have 4 millimeter water drop. Then you break it into 1 millimeter water drops. But you don't know how many water drops, right? Actually, you can calculate that. If you can, let me know how many water drops. You have a large water drop of 4 millimeter radius. You break it into 1 millimeter water drops. They just say the first step is you have to figure out how many water drops. First draw this. Then if you can, how many? No. How many water drops can we create using this volume? We are not remember that, right? We cannot like divide the area. Sorry, I mean radius. So what do we separate? We separate the volume of the total volume, right? Not the radius. Understood? We separate the total volume. Do you understand that? You make water drops out of volumes, right? Or the mass, right? So how do you find the volume of this? 4 over 3 pi. You don't have to convert. 4 cube. 4 over 3 pi r cube. That's the volume of this large one. Equals to volume of this each drops. So let's say for a 1 drop, what's the volume? 4 over 3 pi, 1 cube. So how many do we have? Simple n. You need to figure out simple n, right? Okay, 4 over 3 cancels off. 4 to the power 3 is what? 16, 64. Okay, so do you realize that you can make 64 small drops but we feel like it is 4, right? But it is completely the opposite. We can make 64 number of, that's why you have to separate the volume, right? Okay, so we are making 64 small parts, small drops. Take that down. Thumbs up if you have no issues. I mean, if you have taken this down. Right. So let's say, okay, let's say here the area is A1, here the area is A2. So how do you find the area here? What's the equation? 4 pi r squared, right? 4 pi, what is r? 4 squared. This is cubic, square millimeters. So what do we have? 4 pi, 4 squared means 16. That is A1. Then let's say A2 is what? 4 pi. For a small sphere, area is what? 4 pi 1 squared. Then there are 64 small drops. This is for a one drop. There are 64. So what do you do? 4 pi times what? I'll put 64 here. So to find the area, energy, what you need is change of area, right? Change of area. That's the increase of area. So what is that? A2 minus A1. So you have what? 4 pi 64 minus 4 pi 16. So you get 64 minus 16 is what? 48. So that is the increase of area. This is square. Actually, this is square millimeter. Sorry, square millimeters, right? So once you calculate the increase of area, then it is easy. Then what do you have to do? W equals delta equals, if you want that, delta equals TA, right? T delta A. Here you know that there's only one free surface, right? So you don't have to double this value to find delta A. Understand? This is a liquid drop. So it is on liquid to air. One free surface, you don't have to multiply this by 2. Let's say you have like soap bubbles. Then you have to multiply by 2. You need to find this, then multiply by that 2, then substitute it here. Here you don't have to. Why? Liquid drops. Okay, so what is the surface area? So this is water, right? Surface area, we'll keep this value times this 4 pi 48. You need to multiply this by what? You have to convert this into meters. If you want to find this in joules, multiply this by 10 to the power minus 3 squared, 10 to the power minus 6. So you will get a value something like this, right? You have to solve these problems again at home, okay? For now, just take this down because we don't have time for the simplifications. Please again try this at home, okay? So this much of energy. Once you take it down, thumbs up. Jehansa, I've done. So this note, it is a well organized note, right? So you have to study this at least like 3 times, okay? And do this, try these questions. Then you will see that you can do those exam questions as well, okay? Even by your own actually. But first you have to understand this theory note first, right? Right. Below this, write down, when surface area decreases, when surface area decreases, comma, surface energy, surface area decreases, surface energy decreases. Decreased energy could convert into decreased energy could convert into heat, could convert into heat. So the opposite also can happen, right? Small liquid drops can form a large liquid drop, but their surface energy decreases, meaning surface energy decreases. That decreased surface energy has to convert into something, right? Something in some energy form. Mostly it is converted into energy, right? I mean heat, right? They cannot, I mean, at usual cases, it cannot convert into light energy, right? It converts into heat. It cannot convert into light, right? Right. Below this, write down example. Forming a large liquid drop. Forming a large liquid drop by collecting a bunch of small liquid drops, by collecting a bunch of small liquid drops. Right. So another question, Q. Write down. Find the surface energy released. Surface energy released when forming a large water drop. When forming a large water drop by collecting eight eight small identical eight small identical drops, 8 small identical drops of 0.5 millimeters. 0.5 millimeters. So you have 8 small drops, right? These are small drops. 0.5. How many? 8. Here the how many is given, right? How many? Then what do? You make a large one. Here what you have to find is radius. Similar to the previous one, right? What do? You need to equate the volumes and just find the radius first and let me know. Draw the sketch, then find the capital R. Find the radius and let me know. Yeah, 1 millimeter. Correct. So how do you do? 4 over 3 pi, small one 0.5 cube. How many? There are 8 such volumes is equal to this large volume. 4 over 3 pi r cube. 4 over 3 pi cancels off, right? Then we have r cube equals 0.5. Cube times 8 is what? 2 to the power 3. Okay. Then take the cube. Root. Do we call root? I don't know. So take the cube 1/3, multiply by 1/3. The power, right? We have 0.5. Multiply by 1/3. We have 2. Understood? 0.5 times 2, that is 1 millimeter. Okay. So you can form a 1 millimeter water drop using 8 0.5 millimeter drops. Okay, that is done. Here what has happened? Area has decreased, right? Here you have to find the decreased area, then apply T times delta A. If you can find that. Try that, right? Separately find areas. Here A1 4 pi half, I'll write it as 1 over 2 square. There are 8. Don't convert into meters here, right? Once you find delta A, then you can convert into meters. Otherwise it gets complete. I mean, everywhere there's 10 to the power minus 3, right? Okay, 4 pi half 8. What do you have? 4 pi 2 square millimeters. A2 4 pi 1 square millimeters, that is 4 pi square millimeters. Then find delta A. What is the larger one? This is larger one, right? This minus this. Here larger, here is smaller. So A1 minus A2. So we have 4 pi 2 minus 4 pi 1. So we have 4 pi 1 square millimeters. Then apply delta E. So delta E is equal to T times delta A. Here also you don't have to multiply by 2 because liquid drop. For a solid drop, you multiply by 2. Here liquid drop. So surface tension minus 6. So this is equal to 90.4 times minus 8 joule. Again do this at home, right? For now just take the answer. The simplification you must practice, right? In the exam they ask them. We are only skipping that part because we don't have that much time, right? So the answer should be 90.4 10 to the power minus 8 joule. So this much of energy has released as heat when you break this, when you collect this into a large drop. This much of energy released to the surrounding. Thumbs up if you are done. Try this again at home, okay? Thumbs up if you're done, right? Okay. Below this, put an asterisk mark, then write if total free surface of a liquid is capital A, if total free surface area of a liquid is capital A, surface energy contained in it, comma, E equals TA, right there, E equals TA. So here you don't need, write that, here you don't need increase of energy, right? So when you take a liquid drop, and let's say you consider the, let's say you need to find the surface energy. So what do? Just multiply T by the area of this. Understood? Right? We'll do a question, another question. Write Q, write down. Find the total surface energy. Of a soap bubble. Find the total surface energy of a soap bubble with radius 2 millimeters. With 2 millimeters. Done. Find the total surface energy of a soap bubble with radius 2 millimeters. So here we need surface tension, right? Can we use 7.2 10 to the power minus 2 here? You can't, right? Because this is not water. Not only water, there is soap as well. So the tension value has changed. So they have given that within brackets, right? Surface tension is actually surface tension has decreased. Within brackets, you have to use this value. Previous value 7.2. This one 2.5. You have to pay attention to those as well, right? Okay, so T equals 2.5 10 to the power minus 2 newtons per meter within brackets. So what's the specialty about this? You can draw this sketch. This is 2 millimeters. There are 2 layers. Understood? So this is total area. So when you are finding area, what do you have to do? You have to multiply by 2. Okay, T is what? 2.5 10 to the power minus 2. Here, area of a sphere, this is sphere, 4 pi r is 2 is squared, 4 pi r is squared times 2. Why? Area is total, you need to get the total area. You need to consider both surfaces. There are two surfaces, free surfaces, multiplied by 2. No, you have to use 22/7, right? At home, when you are doing use 22/7, because you need to get used to those calculations, okay? And in some essay questions, they say pi equals 3. In those cases, you can take pi to be 3, okay? Otherwise, you have to use either 3.14 or 22/7, okay? But in essay questions, they sometimes they say pi equals 3, okay? So at home, don't use 3, okay? Get used to 22/7, right? I'll just give you the value, but the value should be this much, right? 2.51 microjoule. 2.51 microjoule. For now, just take it. Okay. Here the difference is you didn't need delta A. Okay. So you are just finding a one sphere. There's a one sphere. You find the energy of that. Right. Below this question, put asterisk mark. Asterisk mark. Write down any liquid is trying. Any liquid is trying to keep its surface energy to keep its surface energy to a minimum. To a minimum. Right? Full stop. So you know, in mechanics you have learned any system is always trying to keep its potential energy or the energy to a minimum value. You have learned that, right? To a minimum value. That's why there are three types of equilibriums, right? Neutral, unstable, stable. That's why the objects fall down, right? As it can decrease its potential energy. So that is a universal law, right? Any system is trying to keep its minimum energy level as much as possible, right? So here as well, we have the surface energy. In a system, I mean, let's say like a water drop. That water drop is trying to keep its surface energy to a minimum value. Okay. That's why those water drops take a spherical shape. They take a spherical shape. Because when you consider any volume, let's say you have a volume like this. I mean, there's some water mass like this. But this has a larger surface area. If you try to decrease the surface area, what could be the shape of this? the shape of that must be a sphere. So a sphere has the minimum surface area, right? That's why soap bubbles takes the shape of a spherical shape. Otherwise, it could take the shape of like a what, cube. Soap bubbles. Have you seen cubic soap bubbles? Because a cube has a same volume, right? Cube has a cube and this one, let's say they have the same volume, but to keep this volume to a minimum surface area, it has to take the shape of a sphere. That's why soap bubbles are spherical. Okay, write down, full stop. This is done by keeping the area, surface area, to a minimum. Therefore, free falling water drops, comma, soap bubbles takes spherical shape. Understood? So you might say water drops. Normally you have seen it like this, right? I mean, like this shape. This is because of the wind, right? There are winds. As it falls down, it's like, it's like this, right? Because wind and there's air resistance. But if we neglect all those and consider a water drop free falling, it takes a perfect spherical shape. I don't know whether you have seen them like in a satellite, right? If they release some water, they quickly take the shape of a sphere because those are free falling objects, right? The thing is air resistive forces are higher than the surface tension forces, so they take the different shape, right? Air resistive forces are, effect of air resistance is higher here, right? It is not only free falling, right? If there's no air resistance, then it can take the spherical shape, right? Okay, within brackets right below, within brackets right, a sphere has the minimum surface area. A sphere has the minimum surface area for a given constant volume. For a given constant volume. Right? Okay. So far we have done surface tension in terms of force, in terms of energy, right? So to explain the phenomena under surface tension, you can use either force, either energy, right? So the spherical shape you can either explain using force or either using energy. Energy, explaining using energy is easier. That is spherical shape, right? Okay. Then we have to think about a few applications under surface tension. Write down the subtopic applications. Applications. Under that, write first one, tension of a string loop on a soap layer. Tension of a string loop on a soap layer. Right. First, take this down. Quickly take the note, right? When a string loop is put on a soap layer, comma, surface tension forces are applied. Surface tension forces are applied inwards and outwards, on the string. Full stop. To the same line, right? When the middle part is punctured, comma, loop takes a circular shape. Full stop. Reason is that surface tension forces on the loop acting outwards and perpendicular to the string. Outwards and perpendicular to the string. Okay. Listen carefully. This also is really important, right? This is a somewhat a lengthy lesson, but I'm trying to do this within like 2 days, right? Usually this takes like kind of like in the usual class, it takes like kind of like could be like 4 or 5 days, right? But if you can cover it within like 2 days, it's going to be really advantageous for you, right? Right. Listen carefully, okay? So in that paragraph, this is what explains, right? So you have a wire frame. Then what do? You make a soap layer. Then you get a string loop. What is a string loop like? Take a string and you knot the ends, right? So you can make a loop. Then what do? You just put it on this soap layer. It could take a shape like this. It doesn't have a specific shape. It could take a shape like this. Understood? So you have the wire frame. Then you make a soap layer. Then take a string loop. You put it on carefully, right? Without breaking the soap layer. So you have soap layer here, and soap layer here. Then it just remains like this. What about the surface tension forces? they are acting everywhere on the string perpendicular to the string, both inwards and outwards, both inwards and outwards. And you can see those forces are balanced, right? This is balanced by this is balanced by this. So the loop remains like this. Okay, quickly draw this one. Thumbs up once you're done. So inside and outside, soap, right? Soap, water. So you need to remember this like a story, right? Like a story. Okay. So here soap. Others done. Thumbs up, right? So here you have soap. Here also soap. So it just remains like this. Then what do? In the middle part, you puncture this. This part, you remove that. Then soap is only at the outside of the loop. Then what happens? This string takes a spherical shape. Why? Now the surface tension forces are present only outside, right? Inward forces are gone, right? Here now air. It is air here. Outward only there's a soap layer. So you know these surface tension forces are perpendicular, right? To each other. Then what happens if you all over the you pull it from all the sides equally? Then it takes a circular shape. This is not a sphere, right? This take a circular shape. Do you understand that? It remains like that, then it becomes a circular like this. Once you puncture the middle soap layer, draw this one. Right. Now listen. Here, the soap layer, string is just put on that. String is not stretched. Here the string is not stretched, right? But here the string is pulled outwards. So what happens to the string? It gets stretched. So there is going to be a tension in the string. This is not surface tension, right? You know, string, in the string, a tension builds up. Here, let's say capital F. Everywhere, right? Everywhere, all over the string. Let's say capital F. These are not surface tension, right? Surface tension is over the layer. These are tension inside the string. Awesome. Write F as well. Okay, below this one, write down. Below this one, right? This causes a tension within brackets capital F. I use capital F as the tension, right? Because surface tension also I used capital T. Okay. Write down. This causes a tension within brackets capital F. Tension capital F in the string. Tension capital F in the string. Full stop. If the string is elastic, if the string is elastic, its length increases. Its length increases. If the string is elastic, its length increases. So what does it mean? Let's say this string is made of like a rubber, right? So what happens? It doesn't remain like this. It further expands, right? Still keeping the circular shape, it further expands, right? If it is elastic, means made of like rubber. Got it? Extensible. If it is extensible, it further increases. Okay, below this, write down. Below that sentence, write down. Consider the equilibrium of half of the loop. Consider the equilibrium of half of the loop. Okay. So in this case, we are going to get an expression for the tension, not surface tension, right? Tension of the string. So to get the tension, we cannot consider the whole string loop. What do? We consider only half of that. We only consider the half of that. Because if we consider the whole string loop, all the forces cancel off, right? Then it becomes 0. Because of that, we use only half of that, right? Half, only half, right? You just cut it from the middle, then you get only the half of the string. Here you have air, here you have soap. So from the soap side, you have these surface tension forces. It is like perpendicular and everywhere, right? Let's say radius is simple r. So this cut part, here it is separated, right? You can see these surface tension forces cause a force to this side. But it is balanced by this capital F. Those are tension in the string. Capital F. Understood? By these two forces, total force created by these surface tension forces are balanced. Take it down. Just draw this one. Thumbs up once you're done. I think you understand that, right? If not, ask me. So this is a bit complicated lesson, right, compared to other lessons. But if you're like cover this earlier, it is going to be really advantageous for you, right? Okay. So this is tension here built in the string. Tension here built in the string. So you can consider the equilibrium to this side and to other side, right? So what happens? The net force, resultant force created by these surface tension forces is balanced by these two tension forces. So you can write 2F equals T times 2R. You multiply by 2 again. Why? There are two surfaces, right? Because this is a soap layer. Soap layer has two free surfaces. That's why you multiply by 2. Then what is this? T times length. That is how we find the surface tension. Surface tension force. Because force is equal to TL. You multiply that by 2. Okay. So do you understand, like this force, you can get components to this component, and there's an exact component to the other side, right? At the other side. So these two cancels off. But these forces adds up, right? So you can see only we have to consider the horizontal forces to this side. Here the thing is, you need to multiply by tension by the length. Here the length is considered as 2r, this length, not 2 pi r, right? Not the length of the circumference. Do you understand that? You need to project each of these forces, each of these surface tension forces. It projects into what? It projects into 2r, right? R, 2r. Not 5r, right? Not 2 phi r. Divide by 2. You can take 5r. Half of the circle is 5r. You are not using 5r. You are using what? You are using r plus r, 2r. Understand that? Because you are only considering a component of this, not the whole force. Force is perpendicular to this one. But this component cancels off. You only consider this component. Then you project it onto the diameter. Project it onto the diameter. Do you understand that? That is all you need. You just think you're projecting all these forces onto this diameter. Right? So the diameter is 2r. That's why this TL, L becomes 2r. Then you multiply that by 2 because there are two free surfaces in a soap layer. So you have this equation. So what we need is force. So F equals 2 cancels off 2 TR. You don't have to remember that, right? So when you get a question, you need to build this from the scratch, right? These are not that much complicated, right? Like once you're doing questions, these are not that complicated, right? Take it down. If you're done, thumbs up. Navindi, are you done? Right, I think it is clear, right? This is the important part here. Actually, this one you have to understand. This is the only new part, actually. Earlier, you haven't learned this one. Earlier, you haven't learned this one, like T times 2R thing. Anywhere else, you haven't learned that. In the surface tension, you learn this. When you need to take the length, you consider the t times projected length. This is called projected length. If you like, project this one here and add all those, you get this diameter as the length. Understand? Here write down simple r arrow, radius of the loop after equilibrium, radius of the loop after equilibrium. Okay, below that write down here the surface area of soap layer has decreased by pi r squared pi r squared times 2, right? Because there are two layers. Understand? So when you puncture this middle part, this pi r squared, right? This part is like removed. But there are two layers, top and bottom layers. That's why pi r squared times 2. Below that, right? Therefore, surface energy decreases by how much? Delta E times T delta A. So it is pi r squared times 2. Understood? Delta equals T pi r squared times 2. Okay. So up to now, I think it is clear, right? So here there are many parts, like many in-depth facts you have to understand, but you need to again and again you need to study this note, right? If you want to understand those in-depth parts, right? Then there's another kind of like main topic. Actually, it is under surface tension, kind of like a main topic and a new concept. Write down contact angle. This is really important, right? This is another new concept. Write down contact angle. Symbol is this 0, like this. So before learning about contact angle, you need to know some of the kind of like some points, right? Right. You might know this. Write down cohesive forces. You might have learned this in like O levels. Cohesive forces. Write down cohesive forces. In front of that, right? Attractive forces between the same type of particles. Attractive forces between the same type of particles. What are they? If you consider like water, if you have water and water, then two particles, both are water. Then those are called cohesive forces. Then if you have two glass particles, those are cohesive forces, right? Understand? Then below that, write adhesive forces. Adhesive forces. Write down attractive forces. Attractive forces between different types of particles. Attractive forces between different types of particles. So what is that? Kind of like a glass particle, water particle. Okay, water particle mercury, or a water particle sugar particle, right? Those are called adhesive forces. Cohesive forces, adhesive forces. So those are the main types of actually intermolecular forces, right? Right. Below this, quickly we'll take the note. Below this, write down cohesive forces. Cohesive forces between cohesive forces between two water particles. Cohesive forces between two water particles is less than adhesive forces between a water particle and a glass particle. Adhesive forces between a water particle and a glass particle. To the same line, right? Therefore, when a water drop is placed on glass surface is placed on glass surface, comma, it spreads over the surface, comma, water wets glass. Water wets, right? Water wets glass. Okay? Right? So what does it mean? So you have seen that, right? When you put a water, I mean a small amount of water on a glass surface, actually it wets the glass surface, right? Like this. It sits on the glass surface like this. Why does that happen? So here you have water molecules, particles. When you consider a water particle and a glass particle, between these two particles, attractive force is higher compared to the attractive force between water particles. Okay? Between a water particle and a glass particle, it is a adhesive force. This force is higher. compared to the force between water particles. Force between water particles. So what happens? Glass attracts water. Glass attracts water. Right? That's why we say water wets glass. Later again read that sentence, you will understand better, right? Okay. Then the next point, write down. Cohesive forces between two mercury particles. Cohesive forces between two mercury particles is more than adhesive forces between a mercury particle and a glass particle. Therefore, mercury does not, mercury does not wet glass. Mercury does not wet glass. Full stop. A mercury drop takes the shape of a sphere. Take the shape of a sphere on a glass surface. On a glass surface. Okay. So have you seen a mercury drop on a glass surface? Even in like a video? Mercury drop in on a glass surface. Like this, right? Understand? Here what has happened? Mercury particles has a higher attraction compared to the mercury and glass attraction, right? So glass particles can't pull these mercury particles into the glass, right? Into means towards the glass. This attraction force is higher among mercury particles, right? So they make a shape like this, right? Like kind of like a spherical shape. The attraction between mercury particles is large. Glass particles can't attract that attractive force among the mercury particles. So we can say adhesive forces are less stronger compared to the cohesive forces. Understood? I think you understand, right? Thumbs up if you understand that. Do you understand that? Okay. So that is all you need to know about cohesive forces and adhesive forces, right? Okay. So water takes this sample on glass, this shape on glass. A mercury drop takes this shape, kind of like almost a sphere, right? So what we are talking about is contact angle, right? So what is contact angle? You can draw a line like this. Then you draw a tangent to this point. We call this contact point. Contact point, right? you draw a tangent to the contact point, I mean along the surface of the liquid. The angle between these two is what we call contact angle. You can see for water on glass, contact angle is an acute angle, less than 90 degrees. Here, what is the surface? Contact point. If you draw tangent to the liquid surface at this point, the tangent goes like this, right? You can see for mercury, it is an obtuse angle. So it is greater than 90 degrees. Draw these two. Below the sentences, draw these two. This is tangent, right? Tangent. Thumbs up if you're done. Thumbs up if you're done, right? Right. Below that, right? The angle measured, the angle measured, the angle measured through the liquid, the angle measured through the liquid between the solid surface, between the solid surface and the tangent drawn, tangent drawn to the liquid surface, tangent drawn to the liquid surface at the point of contact, at the point of contact is the angle of contact, is the angle of contact, within brackets use the symbol, right? Is the angle of contact, use that symbol, comma, comma, between the solid and the liquid, between the solid and the liquid. Right. So how do we figure out the contact angle? This is precisely explained that in that sentence. Okay. So what is that? Okay. The angle measured through the liquid. Angle measured through the liquid. Through the liquid, right? Not here. You have to measure through the liquid. Okay. Remember that. Here as well, through the liquid. Underline through the liquid. Between the solid surface. So solid surface and the tangent drawn to the liquid surface at the contact point. So this one liquid solid surface and the tangent through the liquid, not this angle, right? This is not through the liquid. You have to measure it through the liquid. Understand? Here as well through the liquid, right? So that is the contact angle by definition. Right. Below that, right, separately, when a liquid is put into a tube, when a liquid is put into a tube, comma, like under that, right, first point, if benzene if benzene if benzene is in contact with if benzene is in contact with clean glass clean glass, comma, adhesive forces are very strong. Adhesive forces are very strong, causing the meniscus, you know the meniscus, right? Causing the meniscus to be hemispherical. Meniscus to be hemispherical. Within brackets, contact angle is 0 there. Okay, I'll explain this. Then the next case, write down contact angle between clean water and clean glass, like this, approximately equal to 0. Write this down. This is mean approximate, right? Approximately equal to 0 degrees. Then another point below that, right? If adhesive forces are not that strong, comma, this contact angle, use the symbol phi becomes an acute angle. Phi becomes an acute angle, and the meniscus shape becomes becomes concave. Meniscus shape becomes concave. Okay. Another point. Write down. If cohesive forces are stronger, if cohesive forces are stronger than adhesive forces, if cohesive forces are stronger than adhesive forces, phi becomes an obtuse angle. Phi becomes an obtuse angle. To the same line, write meniscus. Meniscus is convex. Meniscus is convex. Okay, meniscus is convex. Then write another point. If pi equals 90, phi equals 90 degrees, meniscus is plano. Plano means like a plane, right? Like plane means horizontal, completely. PLANO, right? Plano. Sorry, NO. You know plano, right? In light you have learned that. Plano convex, plano concave, remember? Those are just shapes, right? Okay. Now I'll explain that. What is the first point? So we have benzene. Now we are considering about tubes, right? Like glass tubes. We are thinking about glass tubes. Don't draw this. You take benzene. Don't draw it, right? Benzene, and you take, you immerse the glass tube like this. So what happens is, there's a rise, capillary rise. Didn't go for the capillary rise yet. In the first case, they say what? Now this benzene and glass, adhesive forces are stronger than cohesive forces. So let's say you have benzene here benzene, right? Here you have the glass tube. Adhesive forces means forces between benzene particles and glass particles. They are very strong than cohesive forces between benzene particles. So what happens? These particles attracts strongly to the glass. So what happens is, these particles tend to climb over the glass surface. And finally what happens is, this takes a kind of like a hemispherical shape. You can see these particles very glass, for benzene, glass is very attractive, right? That's why the liquid surface inside the tube is not like this, very attractive. Then they are trying to like climb the glass surface. And this first, they take a hemispherical shape. They take a, the meniscus takes a hemispherical shape. If the glass tube is like this, for the first case, right? hemispherical shape. Glass is like very attractive to the benzene. I mean, benzene climbs like and make a hemispherical shape. Then what is the contact angle? How do you measure that? You have the solid surface, contact point, draw the tangent. When you draw the tangent to a hemispherical shape, what happens? That tangent also goes through the solid surface. Then the contact angle is 0. Understand? Contact angle there is 0. So this is for the first case. Here benzene, you have the benzene. Then if you put water, at the next tube you put water. Right? It is almost hemispherical. It's almost like this. But it is like 1 degree, it could be 1 degrees, 2 degrees. Right? In practical cases. So that's why we say contact angle is almost 0 for water. Water and glass tube. Okay? Let's say if we have something like mercury, let's say mercury. What happens? Mercury particles, they are very attractive, right? They attract towards the liquid. Then it takes this shape, mercury. Then what is the contact angle? Between this one and tangent drawn here is this one, right? 5. So you can see this 5 is greater than 90 degrees, obtuse. If you have like a plane surface, and this is convex, right? Convex. This is concave. If you have a planar surface, then you can see what is the contact angle? 90 degrees. So depending on the liquid and the material, they can have different shapes. Right? Below the note, draw these 4. If you have done, thumbs up. Here hemispherical, right? Hemispherical. Here concave, convex, plano. If you are done, thumbs up, okay? Your answer? Right. Then write the subtopic, find in contact angle. Find in contact angle. Find in contact angle. Okay, listen carefully. I'll just briefly give you the. So you take something like a glass, like a plate. It could be a glass plate or it could be like an iron plate, okay, or metal plate, let's say. You just immerse that in the liquid. This could be water, could be mercury, okay. You immerse that vertically, right? Immerse that vertically. So let's say if this is water, if this is water, you have to incline this plate till, so you can see this surface is not completely horizontal, right? This surface, there's kind of like a meniscus here, depending on the liquid. It could be to this side or it could be to other side. Okay. So when you tilt it, you have to tilt it till one side becomes completely horizontal, right? Completely horizontal. Okay. Then, so this is the solid surface. This is the liquid surface. Then you can mark the contact angle. By definition, it is the angle between tangent and the solid surface, right? So you can easily measure this angle. When one side of the liquid you make, this can be done by tilting the plate, right? So this becomes contact angle. So experimentally you can find the contact angle. So for the other side, the shape would be like something like this. This angle, it is difficult to measure, right? This angle. But when you make a one side horizontal, by tilting this, you can easily measure the contact angle. This is for water. This is for water. Then what happens if you have mercury? Actually, for mercury, this side, for mercury, contact angle is a obtuse angle. So for mercury, this becomes the contact angle, and the other side gets a shape like this. Measuring from this side is difficult, right? So what do? We tilt this. All we do is we tilt the metal plate or glass sheet till one side becomes horizontal, completely horizontal, and then measure this angle. Then that must be the contact angle for that liquid, and between the liquid and the this sheet, right? Okay, draw these three images. Here the P point is here. Here the P point is here. The opposite side, right? Draw that. This is Mercury. Below that you have to write Mercury. If you have drawn this and write them, thumbs up. If you had complete that, thumbs up, right? Thumbs up if you're done. Right. below this write down. First, a plate is immersed. A plate is immersed in the liquid. In the liquid vertically. In the liquid vertically. Another point. Incline the plate till one side of the liquid surface becomes completely horizontal up to the point P. Up to the point P. Next point. measure the angle between the plate and the horizontal liquid surface. The plate and the horizontal liquid surface. Okay. Then write down another subtopic. Marking surface tension forces. Marking surface tension forces. So like when you are doing problems, you have to be able to correctly mark surface tension forces under any circumstance, right? Okay, let's consider the first case. Put a point, write down. A glass slide is hanged by A glass slide is hanged by a spring balance. A glass slide is hanged by a spring balance and and it just touches it just touches a liquid surface. A liquid surface, right? So I'll discuss when contact angle 0 and if contact angle less than 90 degrees, if it is acute angle. Okay, let's consider when it is 0. I'm drawing this at two sides, right? Okay. So you have the glass slide, this glass slide. Simple A, simple B. Length is A, thickness B. You just touch, just touch. So you have the liquid here, liquid layer, I mean liquid here. So how do you mark the surface tension forces? Vertically downwards. Understand? You can draw this with me. It is vertically downwards. Why? Contact angle is 0, right? Let's consider this case. Contact angle is an acute angle, so it is not along the glass surface, right? So it has an angle like something like this. It is not, it is kind of inclined, right? Surface tension forces, they are like inclined. Remember that one, if contact angle is 0, surface tension is along the glass surface, right? Here the contact angle 0. Here the same case. But if contact angle is an acute angle, 90 degrees, you have to mark these surface tension forces along that tangent. Draw these two. If you are done, thumbs up. If you don't understand, so tell me, right? If you are done, thumbs up. Once we discuss this topic, we'll stop for here today, right? Johansa, are you done? Right. So you know this is attached to a spring balance, right? So what should be the reading of the balance? Before that, we'll write an expression for surface tension force. So these are T, right? T acts along what? What's the length? Acts at the bottom, right? Bottom surface is like this. A and thickness is B. You need to consider the length. Length around the bottom like this. So T T times length is what? A plus A, B plus B, 2A plus 2B, right? Do you understand that? 2A plus 2B. So the surface tension forces are acting around, right? So the liquid surface just touches the bottom, just touches the bottom. So the liquid, what does the liquid do? It kind of like attracts the glass surface towards the liquid. Here what happens? How do we mark total force here? When we consider, you have to understand these forces are like inclined, right? So here you have the contact angle. Then if you consider the other side also has a same force to this side. Then you have to understand that these horizontal components cancel off. Then what do we have? Vertical component. Then T cos pi. T cos pi. All the horizontal components of these inclined forces cancel off. Important, right? Really important when you are doing questions. All the horizontal forces cancel off. Horizontal components. What is the vertical component? T cos pi. Then all those adds up. Then all those particles, forces are vertically downwards. Then what do we do? T cos pi multiply by the length. Length is what? It is same as before. 2A plus 2B. So this is the total surface tension force. Here, this is the total surface tension force if pi is 0. If pi is the acute angle, you have to get cos pi. You don't remember each of these, right? Depending on the question, you have to be able to write this. Understand? Okay. So when we think about both of these, so what should be the reading? Reading of spring balance should be what? Listen carefully, right? This could be the kind of like the last part for today, but this is really important, right? Pay attention. Reading of the spring balance, what's that? Should be weight of glass slide plus F. Isn't that? Weight of the glass slab plus the surface tension force downwards. Here the same case. Weight of the glass slide plus surface tension force. But here, since the surface tension is kind of like inclined, you need to get the vertical components. All the horizontal components cancel off. Okay, write this down. So this is under the first case, right? Under first case. If you have written down thumbs up, we have to cover a small, just another part, right? So just pay attention. So to continue the next part, you need to have a clear understanding of these, okay? If you are done, thumbs up. Okay, so this is under the first case, right? Then second, write down. First case means just only the bottom part of the object touches the liquid. right? Then second case, when part of the object, when part of the object is immersed, when part of the object is immersed, comma, here let's say this part, I mean this part is immersed, right, in a liquid. Let's say this is 0 and this length is A, this length is B. So how do we get here as well? There are surface tension forces. There, it is like this, right? Downwards, because phi is equal to 0. So what do we get? T times length. Length is what? 2A plus 2B. 2A plus 2B. Here as well there's a reading, I mean spring balance. So what should be the reading? What should be the reading? Weight of object. It reads the weight of objects plus surface tension is downwards, F, right? There's another force here. What is that? Because now part of the object is immersed, there's going to be upthrust. Upthrust is acting upwards, right? Understood? So this must be the reading of the spring balance. Got it? Take this down. If you're done, thumbs up. Thumbs up if you're done. If you don't understand, tell me, right? Yeah, answer you done. Okay. Below this, right? If pi equals 0 for different shapes, this is a small part, right? For different shapes, we consider pi to be 0, then it is less complicated. If pi has a value, right? Phi has a value, you just have to get the cos phi, that's all. Cos phi or it could be sin phi. Anyway, the vertical, depending on the question, right? It depends on the question. So let's say you immerse a cylinder, solid cylinder. You immerse a solid cylinder. So for the solid cylinder, these are the surface tension values. So how do you write the surface tension force? How do you write? T equals, what's the length around it? If the radius is r, 2 pi r, right? T times L, T times 2 pi r. Take this down. Then let's take a external radius capital R, internal radius simple r, cylinder. So how do we write it? Surface tension forces downwards. So at the bottom it is like this, right? So for this internal radius it is 2 pi simple r, external 2 pi capital R. Those are the two lengths. There are T forces like this from the external surface, and on the internal surface also there's T forces downwards. So I have to consider both. So T times 2 pi capital R plus 2 pi simple r. This is the total surface tension force. Then another one, let's say like a coin or something. Let's say you immerse like half of the coin. Radius is r, thickness of the coin is simple T. So how do you write the surface tension? T times, what's the r, then there's a r other side as well. 2r, 2r, 4r, plus there are two thicknesses, right? T, 2t. Understood? But for all these, I just took pi to be 0, right? If there's a pi value, not you just have to take the component, that's all.